Today we have our speaker Abhishek from Princeton. Abhishek is a fifth-year PhD student in Princeton, CS, advised by Sanjeev Arora, and he is also an Apple AI ML scholar. He currently works on developing mathematical models to understand and improve efficiency and robustness of training deep networks. Abhishek actually has this is his first time here at TTIC, but he has a lot of connection to TTIC. He was admitted by TTIC PhD program, but he was not able to bid because of pandemic. We also discussed his papers in machine reading groups. And today he is going to tell some interesting thing about curriculum-based training. Let's start, Abhishek.
Thank you, June, for the introduction. Thank you, everyone, for coming. I'm Abhishek, and I'm from Princeton Language and Intelligence. And today I'll be presenting two works on the lines of efficient curriculum-based training, theoretical modeling through synthetic testbeds. All right. So the current deep learning paradigm is driven by scaling laws, which suggests that more compute means better performance. By compute here, I mean the scale of the model that I am training and the amount of data that I provide during training. And these are the plots from Kaplan et al. In 2020 that try to convey the same on more compute means better performance. However, when you don't have enough compute, then we need to come up with some clever strategies to train a model by simply providing in some more information, more than what your training data can provide. And examples of such training strategies include knowledge distillation, which is a widely used strategy to train small models better when you have access to a bigger and better model. The other kind of strategy is something called context-enhanced learning, more primarily used for language models, where we simply add in some useful information to the model in context and hope that the model understands that information as it trains on the training data. I'm going to explain these algorithms in more detail when I explain them in the later part of the talk. But here we'll be focused on two primary questions related to these algorithms. First, how do these algorithms work in practice? And second, if we can understand this mechanism, can we better improve the model design or the design choices to target the success of these algorithms? And the primary theme of this talk will be that instead of giving a theoretical end-to-end framework, we'll build some synthetic test beds and understand the behavior of the models under these algorithms. And we'll pinpoint the critical component of the success of these algorithms to an implicit or an explicit curriculum. And then we can show that we can tune the model choices or design choices better based on our understanding of this curriculum. So without further ado, I'll talk about these two works. The first work is on progressive distillation, which is a variant of knowledge distillation and was presented in ICLR recently. And the second part of the talk will be on context-enhanced learning and will be presented in ICML in July. All right. So the first part of the talk is progressive distillation induces an implicit curriculum. And this is joint work with Bingbin, Sadika, Andre, and Survi, a collaboration across Princeton, CMU, and UPenn. All right. As I said before, the motivation of knowledge distillation is to train a smaller model as a student better when you're given access to a bigger and better model which behaves like a teacher. When you don't have access to such a teacher, what we usually do is apply a cross-entropy loss on the student's predictions and the true label given by your training data. But when you have access to a teacher, what we do is we apply a scale divergence loss between the teacher's predictions and the student's predictions. A bit of machine learning 101 here. What we mean by predictions here is that the model processes the input through a sequence of its layers, computes logics, and then applies a softmax to compute scores for different classification classes. One, in general, could apply some temperature term to the teacher's predictions, to smooth out or make the predictions more spiky. But we are not going to touch on the temperature. Whatever we're going to present will be independent of the temperature that we apply. Alright, so knowledge distillation has been known to often lead to a better student, more than like just training on training data. But what has been observed in practice is that a better teacher need not always lead to a better student. And this is a plot from the 2020 paper that showed that in computer vision tasks, in some computer vision tasks, with increasing performance of the teacher, the performance of the student did not show a monotonic behavior. And this has been also recently shown for language models as well from this Apple paper in 2024. So a common mitigation strategy instead is progressive distillation, where instead of simply using one teacher checkpoint to supervise the student, we'll use a set of teacher checkpoints that we store during the course of training. By that, what I mean is like during the training of the teacher, we save n teacher checkpoints. We split the training time of the student into n intervals. And in each interval, we'll supervise using the corresponding teacher checkpoint. So in interval 1, we'll use the supervision of checkpoint 1. In interval 2, we'll use the supervision of checkpoint 2, so on and so forth. Now this is in contrast to one-shot distillation, where you simply use the final teacher checkpoint to supervise the student. Now both variants of progressive distillation and knowledge distillation has been used in practice across a wide variety of applications. But most notably, progressive distillation was used by Google DeepMind to train Gemini 1.5 Flash from Gemini 1.5 Pro. Although they do not give out the details on how they did it or what the details behind the progressive distillation framework, what this showed is that this model outperformed a bunch of existing pre-trained models across a wide variety of tasks. So in this paper, we take a deeper look on progressive distillation and one-shot distillation. In fact, the underlying question that we ask is like, how could intermediate checkpoints could help? And there has been a lot of work in prior studies that tried to understand this question, but they took a more of a generalization approach. What this showed is that if we have access to the intermediate teachers, then we can reduce the learning gap between the student and the teacher, which can decrease or which can give you better generalization bounds on the student after training. But given the current scale of deep learning, all the generalization bounds turn out to be trivial. And so a lower trivial bound does not give you much information. On the other hand, we take an optimization perspective. And we want to formalize the intuition that if we have access to the teacher's trajectory through its intermediate checkpoints, we should be better able to guide the student. And that should give us some optimization benefit. We extensively studied this on a synthetic testbed called sparse parity, where we show that the prior theory can fail to explain the gain that we'll show. In fact, we deeply study the behavior of NLPs and transformers on sparse parity, on formal languages, mostly probabilistic context-free grammars or PCFGs, and in real-world datasets, Wikipedia and books, and we show in all of these settings that progressive distillation can improve the performance of a small student model compared to one-shot distillation. So circling back to the questions that I asked before on how and what design choices can we train, we asked the following two questions. How does progressive distillation work in practice? And if we can understand that, can we say that do we need to store all teacher checkpoints during training? Or are there certain teacher checkpoints that are more important for the success of progressive distillation? And at the end of this part, we'll show that progressive distillation helps through an easy to learn curriculum that it can provide through its intermediate checkpoints. And not all checkpoints are important. We'll give you the properties that matter for progressive distillation. All right, so any questions still here before we go into the details? Okay, all right, so let's talk about sparse parity, and we'll extensively discuss our sparse parity in this setting, in this part. So the task of sparse parity is defined as follows. We're given arbitrary random strings containing plus minus ones, and our label is a product of the input coordinates in a sparse support set or a sparse set of coordinates. For example, in the example that I'm showing, the sparse set of coordinates are given by 1 times 1 times minus 1, and so for this particular example, the label will be given by minus 1. And this synthetic task has been studied in prior works, and it has been known that this is a combinatorially difficult problem because of the difficulty in searching for the right coordinate set. In fact, one can show in the SQ dimension framework that the amount of compute that is necessary to learn this task grows exponentially with the size of the support coordinate set for a bunch of popular algorithms like noisy gradient descent, etc. But what has been also known is that bigger models train faster on this task. So this is a replication of our claim where we train MLPs of different width on a specific instantiation of sparse parity. And what we find is that MLPs of width 50,000 can train within 5 million steps, while MLPs of width 100 even fail to learn after 20 million steps. And when models do get successful on this task, they show a sharp phase transition in performance, going from random prediction to true prediction. We repeat these experiments for transformers as well, where we show that transformers with more attention heads train faster because attention heads play the role of search in this task. On the other hand, what we show that a small model, which was a MLP of width 100, which failed to learn before, can now train as fast as the teacher itself using progressive distillation. So you should, on the right hand side, you should compare the green line, which shows the behavior of the student under progressive distillation, and the black dotted line, which shows the performance of the teacher. And you can see that they match, while the student fails to train with one-shot distillation and cross-entropy training. So given that now the model can learn from the intermediate checkpoints, there are some extra signals in these checkpoints that help the model. Question over.
So
Yeah.
can you maybe clarify a bit the x-axis there? So is that the training steps for the teacher, for the student, for both? Like where, what are you distilling from which checkpoint to where and what time?
Yeah. Good question. So here we use batch size 1. So training steps means, and we always get like fresh samples.
Mm-hmm.
So training steps here equals like sample complexity as well. And so for progressive, for training time for teacher would mean like just cross entropy training. Okay. For progressive, we split the training into like we store like at every 100k steps. We store the checkpoints at every 100k steps, and then we train. So for that corresponding interval, we just train with the teacher of that at the end of that step. So for like from 0 to 100k, we'll train the student using the 100kth checkpoint of the teacher.
But for how many steps?
100k steps.
I see. So the number of student steps is the same as the number of steps you use for the teacher to that checkpoint.
Yeah.
Okay.
For now, for this plot. But we'll show later that we do not need to do this.
Okay.
Yeah. Okay. Any questions?
I'm just.
Yeah.
So I understand, but then in that case, okay, maybe this is a bit confused because you said this shows the student and the teacher take the same time to train. It's really what it's showing us is just once the teacher is trained, then the student can also train. I mean, based on the teacher. It's not like, okay.
It's based on the teacher. Like once we have a good teacher, and once we store all the checkpoints, we can train the student as fast as the teacher.
I don't understand as fast as the teacher part.
It's just like same training steps, same, like you require same complexity. So, like you need to
Okay, let's
sample
go on
that
because
many
I don't.
points.
Okay, let's go on. I don't see
Okay,
how
okay.
this plot shows.
Okay. All right. So before going down to analyzing sparse parity, progressive distillation. Yeah.
Very dumb question in the last slide.
Yeah.
Yeah. So you say that okay, the small model which in fast when we have the big models like teachers, right? So I would do something very dumb like this. Given the student that have the same architecture that of other teacher, I would simply copy the weight of their teachers to the student, so that I can done no training, get the same accuracy as the teacher at the very beginning. So
No, but then you have to keep the size of the teacher same as the student,
yes.
right? So now we are training a student which is much smaller than a teacher. A student is of size 100, while teacher is of size 50,000.
So what about this? I do some kind of pruning.
Sure.
So my student will now have smaller weight than the teachers, and then after pruning, I will copy the weight directly to a student, and I will get like the same, let's say approximately the same performance without any training.
Yeah.
So what's
Pruning,
the point of this graph?
No, pruning. Okay, pruning can work, but our point was to understand distillation
Okay.
and not pruning. Like with pruning, there is a follow-up paper that shows that pruning also, you can do pruning in such a way that you do not need to do distillation.
Yeah. Maybe my perspective is different. Trying to see what you define faster here.
Yeah. So
Okay.
by that I mean that we can train the student using the same amount of samples that we require to train the teacher when we're training the teacher with cross-entropy training. That's all we are trying to say here, right? Like we have to sample some data, and now we use the teacher's predictions
Okay.
on those data. And what we mean is that when the student requires only 10 million samples,
Yeah.
same as the teacher when he trained with progressive distillation. Yeah, but you're right. Like pruning can also work. There's a follow-up paper to our work that showed that, not us, by someone else, but they showed that pruning also, you can do some clever pruning and you don't need to train. Yeah.
I'm not trying to compare pruning and distillation. I'm trying to say that, okay, let's say, once we have our teacher models, we can have a smaller models that have this comparable performance of the teachers called student very fast. It should be
So here we are going
intuitively
for 10 million steps.
right things.
But later on when I show another plot, we can train it within 1,000 steps.
Okay.
Okay, that's the design choice question that we'll talk later, but we can train much faster.
I don't know if this is the same question, but is it the best that we can do? I mean, for the student, can the student learn actually faster than the teacher? Because the student look at the full output of the teacher instead of the label, right? So is it the best that the student
No, this is not the best. We'll come later, but this is not the best. Okay, so let's go into the details. So as I said before, sparse parity was difficult because of the difficulty of searching for the right coordinates. But it becomes easy if instead of just having access to the true labels, we had also access to some easier function on the support coordinates. So instead of just having the true labels, say we had true label plus some additional linear function on the support coordinates. Then suppose that the linear component kind of dies over time. Then one can show that the necessary compute can now reduce to being polynomial on the task parameters, because the student can learn the support coordinate, the identity of the support coordinates from the additional component, and then can fit it to the true function. And what we show in our paper that the secret of progressive distillation is that the output of some intermediate checkpoints closely resemble the above easy to learn signal. And to verify our claim, we take the teacher's checkpoints and we probe the output of the teacher's checkpoints. What the probing, as I said before, the teacher shows a sharp phase transition. We show here 3 checkpoints for your reference. One before the phase transition, one during the phase transition, and one after the phase transition. And the probing technique that we are going to use will be a correlation metric that tries to measure the correlation of the output to monomials on the support coordinates. And the thing that you need to remember about the correlation metric is that if this becomes non-zero, that implies the presence of the easy to learn signal that I described before. And so what we did, so when the model transitions, when the model shows the phase transition, the correlation metric spikes, and this is in checkpoint 2. And that implies that checkpoint 2 contains the linear function, contains an additional linear function on the support coordinates. So what we claim is that the reason progressive distillation works is because checkpoint 2 contains a simple to learn linear function on the support coordinates, which help the student learn about the identity of support coordinates faster. And this is what we call as an easy to learn curriculum that the model can provide to its intermediate checkpoints. Any questions here? All right, so then the question is like, are all checkpoints necessary? Well, if the point is like, if the phase transition checkpoints contain the usual signal, maybe we should only include the phase transition checkpoints. And so what we show is that progressive distillation can work with 2 checkpoints. The first, for a fraction of training, we train with the second checkpoint 2, and for the rest of the training, we can switch to the final teacher checkpoint. And in this case, the model now trains much faster, within 2% of what we used for teacher.
Yeah. Is there any combining effect when you combine both checkpoints? The 2 checkpoints is better than 1.
Yeah, so that's a good point. We didn't try. We just simply applied a curriculum where for fractional training, we're training with checkpoint 2 supervision and then in the final checkpoint. Yeah. Any questions? All right. So we extended our analysis to more real-world datasets, where we trained transformers on real-world datasets. And we worked with a very initial version of transformer called BERT in our paper, where the BERT model is tasked to predict missing tokens in the sentence. So for example, for a sentence like the cat masked away quickly, the model is trained to predict the missing word like danced, ran, cried, so on and so forth. And when we train such a model, we see a 3-phase behavior in the model's training curves, and the second phase has a more sharp drop in loss, which is more aligned with the sharp phase transition behavior in sparse parity. In fact, when we probe the model's output over the course of training, we see a change in the model's dependence or behavior on the context tokens when it predicts that mask token. So at the start of training, it uses more short context tokens, so it uses more like cat and away. And over the course of training, it starts using more and more longer context tokens for prediction. And we formalize this behavior using something called n-grams, where n denotes like the words that it uses for its prediction. So using something called a perturbation measure, we show that at the start of training, the model utilizes more 3-gram tokens to predict. So in this case, it will start using more like cat and away at the start of training while ignore the rest of the tokens. And over the course of training, it starts using more and more longer context tokens. In fact, it shows an inflection point in its second phase where it switches its dependence on 3 grams to more 7 grams and 9 grams, so on and so forth. Yeah.
Question. So, do you measure n equal to 1 I'm curious. I'm always curious.
N equals to 1 doesn't make sense, right? Because N equals to 3 is this.
Right, but I'm just curious. Is there like part of decrease of words like validation loss just because it fits to the frequency of English words?
Oh yeah.
Just doing nothing, just fit to a frequency.
That's a good point. We didn't try. Yeah, that's a good point. We just tried 3, 5, 7, 9, so on and so forth. And this is what we call as an implicit n-gram curriculum induced by the teacher. And we show that the student BERT model, which was like 4x smaller than the teacher model, trained much better than cross-interpret training and one-shot distillation. And we also in the paper we have a bunch of ablations trying to study to try to pick the right checkpoints, and we can also show that in this setting as well we can perform progressive distillation with only 2 checkpoints. The first checkpoint needs to be the middle of the second phase, and the last checkpoint needs to be the final teacher checkpoint. And we give all the explanations on formal languages via probabilistic context-free grammars. Alright, so in summary, part 1, we show that progressive distillation can help because of an implicit curriculum, easy to learn curriculum. We extensively study this on sparse parity where the curriculum is given by information on the support coordinates. We discuss then on real world data sets where the curriculum is given by n-grams. And this is the end of part 1. Are there questions on part 1? Alright, so let's move to part 2. So in this part, we had additional information coming from the teacher itself. And then we applied a loss on the students' predictions and the additional supervision that we get from the teacher. The question that we're going to explore in the second part of the talk is, if we don't compute loss on this additional information, can the model still learn to utilize them for training? And that brings us to the second part of the talk on the power of context-enhanced learning and LLMs. This is joint work with Singyu Zhu and Sanjeev Arora at Princeton. Alright, so the motivation of this work comes from humans. We humans try to study on open books, and then we try to do well on closed book tests. The question is, can similar behavior be observed for LLMs, where we keep open books with additional information during training, but can it do well at test time without access to such textbooks? And this will be, here we'll define context-enhanced learning, where we are going to use terms more aligned with language models because we're going to term more language models in this part of the talk. So instead of using cross-interpret training, we'll start talking about vanilla supervised fine-tuning, which is defined as follows. Language models are trained on question-answer tasks, where the loss is computed on the model's predictions and the true answer using a cross-interpret loss called next token prediction loss. And for context-enhanced learning, we'll simply add in some additional helpful information for each question-answer pair, which can be dependent on the question, which can be dependent on the task. But we are not going to compute any loss on the additional helpful context. And note that this additional helpful information is going to be presented only during training.
Just to clarify, you're computing loss also only on the answer, not on the question.
No, not on the question, just on the answer. Okay, so this is an upcoming framework that has been used last year in a bunch of pre-training and fine-tuning settings. I'll try to explain one paper that used this framework. So the setting of the paper was as follows. They tried to fine-tune model on a question-answer based task where instead of just simply giving the question answers, they also added in similar few short examples related to that question answer. And over the course of training, they try to remove the few short examples. And that's what formed the explicit curriculum in their setting. So, for example, let's say our task was to predict the color of objects. And then we can add in like similar examples like sky is blue, roses are red. And over the course of training, we keep on removing those few short examples. Interestingly, their paper called SK Intern showed that they can get like 5 to 10% boosts compared to vanilla supervised fine tuning at both 1 billion and 7 billion scale. So the question is, the three kind of questions that we are going to ask, circling back to the question that we had at the start of the talk, is that how powerful can context enhanced learning be compared to supervised fine tuning? And for the success of context enhanced learning, do we require certain model capabilities? And finally, given that I'm not computing loss on this additional information, does the model learn to verbatim memorize the information, or does it learn to utilize this information for the task at hand? So our contribution for this work was that we designed a synthetic multi-layer translation task. And we showed that on this task, context-enhanced learning can be shown to be provably exponentially more sample efficient compared to vanilla supervised fine-tuning. For the model to do well in this framework, it needs to be ICL capable. What we mean by that is that given that I'm giving you some additional information, the model should understand this information, right? And that's what we define as like ICL capability. And the model and the context and after we get the trained model, interestingly, when you probe the output of the model, we cannot recover the additional information by some likelihood-based strategies. Now, this is significant for a line of AI safety and copyright works, because we want the LLM or language model to learn from privileged information, but not to memorize. And what our work shows is that it can do so if it has the right properties. Okay, so in the interest of time, I'll just describe the first two questions. So let's describe the synthetic multi-layer translation task. In our task, we had multiple alphabet sets which contained generic alphabets, and we contained many rule books or phrase books that contained rules that to convert two tuples of characters from one alphabet set to another alphabet set. And we also had other phrase books as well that connected alphabet set to alphabet set 3, so on and so forth. And the task was defined as follows. We were given strings, and then we applied D layers of like translation. In each translation, we applied two sub-steps. The first step involved a circular shift that moved the string 1 to the left. And then we applied the phrasebook rules to translate two tuples of consecutive characters. So capital BC became like small eb because there was a rule in phrasebook pi1, so on and so forth. And we did for the rest of the translation tasks. Now, so our task was then defined as, given the input string, can you define the output string? And this was a prompt that we used for supervised fine tuning. You are given a sequence, can you give me the output in the final language? And this task can be shown to be a difficult task for vanilla supervised fine tuning, because if you trace back the dependence of characters in the output string, then you can show that each character depends on 2D input characters in the input string because of circular shift. And so we can then again argue from the SQ dimension framework that the family of such tasks will have an SQ dimension of e power omega t, which is exponential in the depth of the translation task. And one can then show for noisy vanilla SFT that it will require exponential sample complexity.
So just to understand, so D is the number of steps here, right?
Yeah.
And your learning those pi 1 through pi d are fixed for all. I mean, those are that's the parameters you're learning. So
yeah.
okay.
Yeah. We'll describe later that we can change the phrase books and whatnot, but we're. So the question then is like, given that it's difficult to learn the parameters of that task, what if we simply provide those phrase books purely in context during training? Does the model learn to utilize them, or does the model, and how can the model learn to utilize them, and does the model learn to like verbatim memorize? Is the question that we are going to ask.
These are the same. All the examples would be with the same. What do you call them? Phrase books.
Phrase books, yeah.
Is that correct?
Yeah.
Okay.
They will use all the same phrase books, but as a part of training, we can change the phrase books as well. But in the end, we are going to test with one set of phrase books at evaluation.
They didn't change. They understand we're changing the phrase.
Okay. I'll explain the steps, and then it will be much clearer. Okay. So let's talk about the experiments for multi-layer translation task. So we have two primary steps in our setup. The first step is to get an open book model, a model that can understand the phrase book information and solve the task. And the second step will be called context enhanced learning, where we now make the model independent of the phrase book information. Alright, so I won't describe the first step, but what we do is that we use multi-layer translation task with like random phrase books, and we get a model that can simply, given like access to the random phrase books, it can try to solve the question answer task with some abstract tokens. Like it's not allowed to give out the intermediate tokens, it can just go from question and then the answer with some abstract tokens in context. So here we get an open book model that given any phrase book in context, it can solve the task. But now in the second step, we're going to perform context enhanced learning, but for that we fix a target set of phrase books. And because the model is now ICL capable, given the set phrase books in context, it can solve the task. But in the end, we want the model to be independent, and it cannot do it because it doesn't know how to solve the task without the phrase books information in context. Yeah.
Can you explain to me the intuition behind it? Because I'm not sure. As in the transformer base, right? So the embedding of S1 here actually contain information. It depends on a bunch of information beforehand. So why the learning? So even though you remove it, you didn't update it. The embedding already had cheating information.
Yeah, it has the cheating information.
Yeah.
And it uses the cheating information to solve the task.
Yeah. So that's why I'm confused. Even though the updating process, but when you actually test, right, the S1 here, imagine when you do the test here, the question here would not have the extra information. So the embedding of S1 would be different in the test. Then how does this actually helpful? Because it's different between train and test.
No. So this is at the start of training.
Yes.
It's not helpful yet. It's not helpful. We're going to do something in this part of training where now it can learn this better without this helpful information, right? And that's where the dropout comes to the picture.
Yeah.
That is correct. Yeah. So again, we want the model to now not depend on the open book materials. So this is how our context enhanced learning actually prompt looks like. We give the instructions, use phrase book, use these rules, use these rules, use these rules, and then the answer is this. And the prediction loss will be on the answer tokens only, nothing on the useful instruction. And what we do is that we just apply random dropout over the course of training. We simply drop in like 20% of the rules and continue training the model.
But again, I'm confused. During this stage, everything is using the same phrase book or not?
This phrase, yeah, everything is same phrase book.
So all the examples, but before you got examples of different phrase books or?
In the step 1, when you want to get an open book model, like when you want an open book model, we train the model using random phrase books.
So you train with the same type of examples?
Yeah, same type of examples,
Right,
random other parameters, random parameters.
Random phrase books,
Yeah.
and still with what you call with supervised fine tuning. So all the time the loss is only on the
Answer
on
tokens.
the answer. Okay, and then you fix the phrase books.
Yeah.
And you continue training with fixed phrase books, and we drop out.
Yes. Yeah, that's all we are doing. And then you're just randomly dropping rules. We're not removing everything. Just remove just 20% of the rules at each step of training. And at evaluation, it's just like SFT. We remove everything and simply ask the model to solve the task without any information. Right. So training is done. Now evaluation without any information.
I'm curious, when you say remove, do you?
And at test time, I do not give the information, right?
No, but also in training time, when you say remove, do you replace with like 0 tokens, or do
No,
you
just remove.
just squish this? So
Squish, yeah.
Okay.
We can do both kind of things, squish or zeros, but squish.
Squish.
Yeah.
Okay. With no indication that you removed something.
Yeah. No
So
indication.
with the dropout, you just have stuff missing.
Yeah. So how does it do in practice? We trained a Llama 3. We used a Llama 3.3b model here, and we showed that with such kind of curriculum training, the model can be at least 10x more sample efficient. But it can, in other cases, in more difficult cases, it can learn while vanilla supervised fine tuning does not.
Sorry, I don't understand.
Yeah. So the green line is the one where we applied just fixed dropout, 20% dropout, and we simply measure with the number of samples that we use in step 2. While this is like just vanilla supervised fine tuning, where we do not give any instructions, where we do not give the phrasebooks information in context.
But what are you counting here? The phase 1, the phase 2? I'm a bit
Oh yeah.
confused.
So here we are just counting for phase 2, the number of samples in phase 2.
Okay.
In phase 1, we do not require a lot of samples. In the paper, we show that it's like with 10,000 samples you can just do it. 100,000 samples you can do it. So we do not add in the y-axis here. But yeah, this is just for stage 2 samples. All right, and
the same phrasebook for testing, the same one as in step 2.
yeah, it's just the same set of phrasebooks. Compare vanilla supervised fine tuning. So we also did a bunch of evaluations, but the main takeaways is that a better dropout curriculum leads to even faster training. Dropout is required during training. Without dropout, the model does not learn to be independent of the phrasebook information. And ICL capability is required before training. Without ICL capability, the model does not understand the phrasebook information, and so it completely fails. So step 1 was important for success. Alright, so the main takeaways is that context enhanced learning can be more sample efficient than vanilla supervised fine tuning. It requires the model needs to be ICL capable to be able to do well, and we also observe some sort of like OOD generalization behavior, where during training we do not need to remove all the rules from the context. We just need to remove like 20% of the rules from the context, and the model still learns to generalize to full removal at test time. Yeah.
I still want to kind of repeat my question. I know that the experiment showed that dropping out the phrase book is helpful, but can you give me an intuition why that helps? Because
Why that
Why-
helps?
yeah,
Why
why
random number? Oh yeah, I'll explain like some theory, like some very basic cartoon of the theory later. Okay, so let's try to understand the context enhanced learning more theoretically, and I'll just try to give some very informal intuition. So previously we showed that vanilla supervised fine tuning will bad because of the SQ dimension being exponential. But in a very toy model setting that was much closer to how LLM performs this task, in a very linear model kind of setting, we showed that there exists a layer-wise like gradient descent based algorithm that can learn this task in like d log t samples. And the theory comes from here. Like, I'll just give you some cartoon on what happens. So, okay, you need to go from the source to the target. And you need to search over different rules at each layer of the multi-layer translation task. And searching for rules in each layer is difficult because there are a lot of possibilities. There are like exponentially more possibilities. But if the model knows how to solve this task by having the context information, then it can simply condition on the steps. But if just one step is missing, then it just needs to search for the missing step. And then the search space becomes linear in the number of possibilities. And so we can show that we can repeat this process only polylog n times and then learn this task more efficiently. And that's what gives you the d log d sample complexity. Because you just need to condition on only the missing rules and then just learn that, and that reduces your search space. Yeah.
So can we say that the model implicitly learned the phrase book and it got it in the web?
Yeah, so it knows how to just read the cheating solution, but then once you start dropping rules at random, it can simply copy it into its parameters. Yeah, that's all that's happening here, context analysis. And we show this in a lot of mechanistic experiments, the same thing. All right, so that's the end of part 2. Context enhanced learning can help an ICL capable model to learn faster. Dropout was necessary for the success of context enhanced learning, and we show, which we don't, okay, I removed slides in the last moment. We showed through like probing experiments that context enhanced learning does not show verbatim memorization, meaning like I can give you the partial rules and I can ask it to autocomplete and doesn't know how to autocomplete. It means that it cannot like give out the rules that I provided during training. Yeah.
And so you presented that as an intuition, but is that, I'm a bit confused as to what's the form, if you have a formal statement here, either based on theory or in...
The last statement?
Well, no. So if you go back
Yeah.
to the previous slide, yeah, here.
Oh, here. Oh yeah, we just, this is just like how we got so this is the main theoretical statement. We created a toy model. We didn't look for transformers. We created a very toy linear model that replicated the behavior of the trained transformer. And on this linear model, we showed that some sort of like layer-wise gradient descent can require like d log d sample complexity to learn this task and not depend on the context information.
But so then, still, I'm a bit confused. The intuition there,
Yeah.
is what you state as intuition is a to me seems like a somewhat specific statement about the mechanism that this happens. And is this something you can actually prove, or is this so that this is the mechanism, that the search space is smaller as opposed to, because I can see other. The thing is that it's not clear you even have to do search because the information is there, like presumably.
You just copy the first iteration.
Yeah, so I'm not sure. This is what I'm kind of.
Oh, okay. I can write on board, I guess. The talk is over, so I can just explain.
Okay, sorry.
more.
Let when you finish
Yeah.
and then.
Oh, the talk is done. Yeah, so I can just explain more on this now. Oh, sorry. Yeah, that was the last slide. But I can explain more on this on the board. A marker.
Oh, yeah.
Okay. So yeah. So basically, what you have to understand is like if you are like if you're giving some context tokens, right? Some information tokens, and you're giving an input x1 to xn prime, right? And now the model has to predict the others, right? Something like this. But now the thing is like because you're training the model to be dependent on the context, it knows how to do this probability of yi given the context and the input, right? But it does not know how to do without this, right? that's what we were saying. Like in the open book model, you can just predict the answer given the context, but cannot do if you remove the context. But what context enhanced learning does is that if you start removing some of the context, now it can copy things into its weight parameters, right? So
Copy is different than search.
no, so the so when there is nothing, right? When there is nothing, then it has to predict y1 to yn given x1 to xn, but it has to search for the parameters that are underlying the x and y, right?
Why? Why does it have to search?
Because there is just one specific set of phrasebooks that connect x to y.
But it has that information. It doesn't have to search for it.
It does not, right? If I am not giving the information,
It has it during training.
it has during training.
Why does the training method has to search? So okay, let me do it this way.
Yeah.
If the training method was not constrained to being gradient descent in a particular model and a particular thing, it would not need to search.
Oh yeah, we are
So-
focusing on gradient descent.
But why is it, so now you have to convince me that that particular training method has to search. Because it's not completely obvious to me that you have to search. Like it's not that any method has to search. Why is it that gradient descent you're saying has to search? Why is it that gradient descent isn't just getting that information and from other steps and internalizing without search?
Yeah, so let me try to rephrase back this question. Like, can you prove that when you provide the entire phrasebook, the gradient descent is not going to memorize this information in the parameters, and it only starts memorization after you kind of like erase, like doing dropout?
That would even not completely convince me.
Okay, that's like a
Yeah, but that's a
Necessary.
start. Yeah.
No,
Or for example, if you did bigger dropout
yeah.
beyond what you can do search on, right? Then is it clear that this is not going to work? Because it's not that all these SQLR bounds are irrelevant. Like you can't get the SQLR bounds are for any method, but you cannot. But clearly there are methods that work here without dropout.
Yeah. So supervised fine tuning, which is like gradient descent, will follow the S2 dimension framework, right? So without like noisy gradient descent. So if you add some noise,
Okay,
then,
that's not what I'm considering.
yeah.
Okay.
But if you don't give me this, right?
No, but
just
I
give
am
me-
giving you this.
Oh no. Okay, that was the confusion. Sorry.
I am giving you this during training.
Okay. Now let's say if I give you this training, then your question is like, why doesn't it memorize that information during gradient descent, right?
Can you prove that it's not? Or can you like analyze that it's not? Or is this just like you're guessing that it's not, or do you have some kind of analysis that says that it's not?
So in the paper, we have experiments, right? So we trained, so after step one, we could do the step one with the target set of phrasebooks as well.
Mhm.
And we can show that if you remove the phrasebooks, or if you just drop
But after
like
step one, you still didn't get the information. It's irrelevant after step one.
no, so you can conduct the step one with target set of phrasebooks, right? Step one we are doing with like random phrasebooks, but let's say I just started training with like C1 star and CN star in phase one, right? So I give all the information, and then we can just we can evaluate the model that if I drop one of them, how does the performance change? And we should see that the model cannot do the task, even with like one drop of rule. That implies that the model simply knows how to just depend on the information and solve the task, right? That's experimental.
It doesn't imply it though.
Sorry.
Yes, but the implication, I don't.
Oh, you're saying that
Maybe
okay,
we'll talk. We can talk. We'll
Okay.
talk about this later.
Oh yeah. No. So we are just doing supervised fine tuning here. I agree that if we had changed the algorithm, would have learned. I agree. But here we're doing the gradient descent based algorithm. Just compute the loss on the answer tokens, and it does not do well. We could have maybe applied loss on the context tokens. It could have learned, but we are not in that setting. We are only in the setting where we're just computing loss on the answer tokens, and we're doing less cross-entropy training.
We'll talk tomorrow.
Okay. Okay, so yeah, I'll just wrap up. Okay, so there are some future ongoing directions that I'm currently working on. I presented to you like two ways of like training, but how do they do head-to-head is a question that I'm still exploring. And for context-enhanced learning is an upcoming framework, and there haven't been much theory depending on like how in-context examples kind of change the optimization trajectory of the model. Yeah, we do, and then can we provide like good supervision techniques based on this theory? Yeah, something that I'm currently working on. All right, that's all. Thank you.
We have time for a few questions.
So for this translation task, I think there are two parts of knowledge. One part is existence of a phrase book. Like, you know, oh, I need to first construct a phrase book and then use this phrase book to translate. And the second part of the knowledge is what's in the phrase book. It seems like your analysis shows the second part is more important than the first part. Like, is that true?
So ICL capability also the ICL capability is also training the model to follow the phrasebook, right? So the first step is trying to teach the model that there is a phrasebook and that task depends on the phrasebook. Yeah, and the second step is more like what's there in the phrasebooks.
Like, I guess I wonder, like, for testing, if you use different phrasebooks, the phrasebooks that are different from the ones used in step 2.
It will. But you provide it in context. Do you provide those phrasebooks in context? Then it will fail, right? Because it just learns with respect to one set of phrasebooks. So it does not know what's there in the other set of phrasebooks, right? But if you provide me, again, additional information on the random phrasebooks, because I had step 1, it can do with a star. It's like, yeah. Yeah. Thank you.